Oh, yeah, it does. Can you go to OBS and fix where the window is? See what I mean?
Mm-hmm.
I think if you change the shape of the PowerPoint window, it messes it up in the live.
Yeah. I did not think those would be correlated. Hi everyone, we're going to get started in a few minutes, so I'm about to sort you all into breakout rooms.
Sorry, there's just like a black line that's gonna bother me forever.
Okay, so it's 10:40, so we're gonna go ahead and get started, and I'm gonna sort you all into breakout rooms right now. So we do expect everyone to be online promptly at 10:40. So do try to come a few minutes early if you anticipate having any connection issues, just because we don't want to have to start 5 or 10 minutes late every day. That takes up a lot of class time after a while. You need to recreate them and divide them in my version. Okay, great. So we're gonna go ahead and get started with day 3. So today we're gonna discuss some basics of how we model atoms and also the periodic table. So first, as we learned in our previous class, elements are substances composed of only one type of atom. So here I have shown is a block of pure iron metal. So this is only made up of iron atoms. But if you think about each atom is defined as the smallest particle of an element that can exist. So this is why an atom is called the fundamental building block of matter. And actually in recent years, we've been able to actually visualize atoms for some of the first times. So here I have an image taken with scanning tunneling microscopy that actually shows individual atoms, which is pretty cool. So let's also quickly review some of the subatomic particles that make up an atom. So inside of an atom, there will be electrons, protons, and neutrons. So an electron is denoted with a symbol of an E and then a minus sign, and it has a charge of -1. And you can also see that it has a very, very low mass. And then we have protons. These are often denoted with a P, and they have a charge of +1. And then on the other hand, there's neutrons. We denote these with the symbol N, and these don't have any charge at all. And it's also worth noting that protons and neutrons have around the same mass, and that the mass of the protons and neutrons is significantly higher than that of the electrons. Just a quick note about units here, that often you'll see people say that an electron has a -1 charge. This is because they put this in terms of the units of fundamental charge, but it's good to keep in mind that in SI units, this one fundamental charge is actually equal to 1.6 times 10 to the minus 19th coulombs. So like we discussed last class, units are really, really important to keep track of. So keep this in mind when you kind of browse through different textbooks, that there are units for charge, but sometimes they'll just call electrons and protons plus and minus 1 as a simplification. So let's briefly discuss atomic structure. So the atom has two general regions. The first one is the nucleus. So the nucleus is made up of protons and neutrons. It's also extremely small. It has a diameter of 10 to the minus 14th meters. And because it's composed of neutrons, which have no charge, and protons, which are positively charged, the nucleus overall has a positive charge. And then we also have the electron cloud. So the electron cloud contains only electrons. And it's actually 5 orders of magnitude larger than the nucleus. So it has a diameter of around 10 to the minus 9th meters. And it also has a negative charge because it's only composed of the negatively charged electrons. So now in your breakout rooms, I wanted you guys to quickly take about a minute and discuss the following question. So which part of the atom has the most mass, the nucleus or the electron cloud? Feel free to, again, also use this time to post any questions in the chat, and we'll do our best to answer them.
Yeah, so there are quite a few of you who are not currently in breakout rooms, so you should have all gotten an invitation, so make sure to accept those. And if you have questions you want to address to me and Katie, make sure you put them in the YouTube chat, not in the Zoom chat.
Yeah, as a reminder, we can't see the Zoom chat once you're in breakout rooms, which is why the YouTube live chat is our main form of communication.
Let's give it a little extra time because there are a few that are just now getting into their breakout rooms.
Okay, so we'll give you about 2 minutes to get settled into your breakout rooms and also think about the question with the members of your breakout room. How are the breakout rooms?
Mostly all but one.
Okay, great. So now that everyone is in their breakout rooms and you've had enough time to answer the question, we're going to go ahead and move on. So which part of the atom has the most mass? If we think back to the table I showed on the previous slides, we can look and see the mass of the electrons, protons, and neutrons. So from here, you can see that the protons and neutrons have 3 orders of magnitude more mass than electrons. So that means that most of the mass in the atom is going to be from the nucleus, just because the nucleus is where all of the protons and neutrons are. So now we want to think about what is the atomic structure for each element. And to do that, we're going to assign a few different numbers. So first we'll discuss the atomic number and then the mass number for each element. And we're going to use the symbol X to denote the filament for an element. For example, lithium would have the symbol Li. So the atomic number, which is also called Z, equals the number of protons. The atomic number is unique for every element. No two elements have the same number of protons. The mass number, which is called A, is the total mass of the atom. Since electrons have a very small amount of mass, usually we can calculate the mass number just by summing the number of protons and neutrons in the element. And then, since atoms are neutral, we know that the number of positively charged protons must equal the number of negatively charged electrons. Because if those two numbers weren't equal, then that means that we would have a charged atom. And in this case, right now, we are only considering neutral atoms. Later in class, we'll talk about how the number of electrons would change if you had something like a cation or an anion, where the atom is no longer neutral. So we can also write this in the form of an equation. So for atomic number, you could represent that as Z equals P. So this is saying that atomic number equals the number of protons. We can also write that the mass number equals the total number of neutrons plus protons. And we can write the third equation, which is the number of electrons equals the number of protons. And then when we represent this, we will write that in the following format. So we have the mass number as the superscript at the top, and then the atomic number as a subscript at the bottom. So we'll go through some examples, so hopefully this makes more sense. But again, feel free to post questions in the live chat. So now I'd like you and your groups to talk about a quick question. So what is the atomic structure of lithium? So here I've given an example of one type of lithium atom. So answer in your breakout rooms the following question. So in a neutral lithium atom, how many protons, electrons, and neutrons are there? And are there any other elements have the same number of protons as lithium? So I'll give you about 2 or 3 minutes in your breakout rooms to discuss this, and feel free to post in the chat as we take time. The chat's up here too. Does anyone need more time? If so, just post in the chat, otherwise we're going to move on in 30 seconds.
More time.
Okay, yeah, so we'll give you another 2 minutes. How are you guys doing now? Do you still need more time, or can we go ahead and discuss the problem? Okay, great. So it looks like everyone has had time to work on this in the groups, so we're going to go ahead and discuss the answer. So for part A, we can figure out the number of protons from the atomic number Z. So in this case for lithium, we have 3 protons. And then from the mass number, we can figure out the number of neutrons. So we know 7 must equal the number of protons plus the number of neutrons. So this means that 7 minus 3 would give us the number of neutrons, which is 4. And then because this is a neutral atom, we know that the number of electrons must equal the number of protons, which in this case is 3. So for part B, are there any other elements that have the same number of protons as lithium? The answer is no. Only lithium can have 3 protons because the number of protons is unique to each element. Okay. So there are also something called isotopes. So not all elements have the same, not all atoms of an element have the same mass. So isotopes are atoms of the same atomic number. This means that they have the same number of protons, but that have different mass numbers. This means that they have a slightly different number of neutrons. So often isotopes of an element are pretty similar chemically and physically, but it's good to keep in mind that they do exist. So here I have shown 2 different isotopes of lithium. So you have one that has a mass number of 7 and that would have 4 neutrons, and one that has a mass number of 6. So this means it only has 3 neutrons. So the periodic table is the way that we organize elements. So if we look at this table, we see that all of the elements are actually organized by atomic number, and then they're also grouped by atoms with similar properties. So we're just going to quickly go over some of the different main areas of the periodic table, just so that everyone's familiar with these words. But we're going to try to go through this pretty quickly, just because these are all definitions. So if we look at how elements are represented on the periodic table, this is the typical format. So you have the atomic number usually at the top left corner. So this is the number of protons, and this is how they're all organized sequentially. Then you have the symbol, the name written out, and then you have the average mass of all the isotopes. So like we talked on the last slide, each element has a whole different number of isotopes. So what we report on the periodic table is the average of all of these. And the vertical columns of the periodic table are called groups, and each group is given a number. The horizontal rows of the periodic table are called periods, and again, each one is given a number starting from top and working our way to the bottom. We can also give different names to different regions on the periodic table. So here in the blue boxes, I've highlighted the main group elements. And here are the transition metals. These are all in the middle of the periodic table. And then down at the bottom, that's kind of taken out from where the transition metals are, is called the inner transition metals. The periodic table also gives us a good way to organize metals, nonmetals, and metalloids. This is important because it's a good way for us to just look at the periodic table and then know some of the properties of these materials. So we know that metals can conduct electricity, they're very lustrous, they're malleable and ductile. And we can see from the picture on the top that all these metals are located on like the left-hand side of the periodic table. And then nonmetals, which are all the way on the right, do not conduct electricity, they're not malleable or ductile. And then we have this small region where they're kind of in between. So these are called metalloids. And they have the appearance of a metal, but they can behave like either a metal or non-metal. So this is the end of our section discussing some of the basics of atomic structure and the periodic table. So we're about to move on to talking about electron configurations. So I just wanted to take 2 minutes and just everyone think of some questions and post in the chat if they have any. If not, we're going to start moving on to talking about these electron configurations. Okay, great. It doesn't seem like there's any questions, so for the sake of time, we're just going to move on, but feel free to keep posting in the live chat, and we can always go back and answer them or address them in office hours. So now we're going to discuss electronic structure. So electrons are located in places called atomic orbitals. And atomic orbitals are defined as the regions in space where the electron has a probability of being located. I saw someone asked what my favorite element was. We can discuss that after class. It's a great question. Is there any particular reason why metalloids are so variable in their characteristics? So a lot of their properties are sort of dictated by the configurations of their electrons. They're sort of at this intermediate region where it's hard to classify them. I think this is a question that is hard to answer without fully understanding all of the different physics behind why elements behave the way they do. But that is a great question. It's good to start thinking about what actually causes these properties. Okay, great. So atomic orbitals are regions in space where the electron has a probability of being located. So this word probability is very important because that means that we don't really know where the electrons are. We just know that they have a chance of being somewhere. And this is why we represent them as sort of this shaded cloud in this diagram instead of like an actual point. Is because we're trying to represent that we don't really know quite where these electrons are. So although in the past I've been representing it as just one sort of cloud, there's actually multiple shells or areas that have different probabilities where electrons can reside in. So here is another depiction where you can see now that there are 3 energy levels that electrons can be in. So these are 3 different areas where electrons could go, and each is made up of atomic orbitals. So for clarity, we're actually going to denote these regions of probability that we represented as shaded areas with a line. This is just so it's easier to represent on paper, but keep in mind that this isn't an accurate representation. We're using a line just because it's easier to draw, but that doesn't mean that we know the electrons are on the line. This is actually a pretty complex topic that you guys will dive deeper into at the beginning of Chem 1A. But I just wanted to make it clear that we're going to represent them as lines, but that we really all need to start thinking about where electrons are in terms of probability, but that's a pretty advanced concept. So we can now think about where the electrons are in terms of energy levels. So the first energy level is defined as the one that's closest to the nucleus. And in this energy level, you can only have a maximum of 2 electrons. And then in the outer energy level, such as level 2, you're allowed to have a maximum of 8 electrons that can occupy each energy level. And in level 3, you can also have a maximum of 8 electrons. So these are something that right now you guys are just going to need to commit to memory, that level 1 has a maximum of 2 electrons and level 2 has a maximum of 8. So This is something that will all come out of sort of the physics that you'll do at the very beginning of Chemistry 1A to really understand where this comes from. But for right now, we can learn a lot about chemistry from just realizing that there are 2 electrons in level 1, and there's a maximum of 8 in the outer levels. So each energy level is actually made up of sublevels. So we can use the letter N to denote an energy level, and then we give them numbers, like I did on the last slide, where we can call them energy level 1, 2, and 3. And then each of these sublevels can be assigned a letter. So by convention, we use S, P, D, and F. And then each of these sublevels are made up of a different number of atomic orbitals. So each atomic orbital can only hold 2 electrons. And by definition, an S sublevel contains 1 atomic orbital. This means that an S sublevel can only contain 2 electrons. And then by definition, a P sublevel contains 3 atomic orbitals, or 6 electrons. For example, if you wanted to draw an N equals 2 energy level, you could draw it like this, where you have a line to represent 1 2s orbital, and then we can also draw our 3 2p orbitals. And then if we filled them with the most amount of electrons that can fit, we would have 2 electrons in the 2s orbital, and we would have a total of 6 electrons in the 2p orbital. And if we add this up, that would give us a total of 8 electrons in the second energy level. So if we think back to the previous slide where we defined a maximum of 8 electrons in the second level, this makes sense, right? We can add up using sublevels the correct amount of electrons in that energy level. So this has been a lot of information. So now I think we'll take another minute to just kind of digest, and then please post some questions to the live chat, and we can always go back to other slides if we want to discuss something further. So these concepts are really hard to understand, but we really think it's important for it to be kind of very fundamentally understood. Okay, so we'll give about another minute just in case anyone has any questions, and then we'll move on to some more material. Feel free to chat and ask questions of people in your breakout rooms too. That's also a great way to interact with everyone and learn. Is there a question in the chat? What is it? I don't see it. Oh, okay. Some elements have high electron numbers and we need a 4th shell. Is the maximum 14? So great question. So in this discussion, I've only considered some of the main group elements, just so we can only talk about S and P sublevels. But there actually are also the D and F sublevels, and those fit even more electrons, which is, so then in some of the outer shells, you do have more than 8 that are possible. So feel free to stay after lecture and we can talk about that further, but just for the purpose of discussion today, I wanted to keep it only to some of the main group elements and just talking about S and P sublevels, just because we're trying to understand some of the basic concepts. Okay, yeah, so I said that there are only a maximum of 8 electrons, but then I showed a slide that had 6 electrons in the P sublevel. What I mean is that there are a maximum of 8 electrons in each energy level, and an energy level is made up of different sublevels. So for example, on the second energy level, We know there's 2 electrons in the s sublevel, and there's 6 electrons in the p sublevel. So these 2 electrons in s plus the 6 electrons in p add up to be 8 total electrons in the entire second energy level. So when I made that statement about the maximum of 8 electrons, I'm talking about maximum of electrons per energy level. But we can break that down further and talk about how many electrons are each sublevel. Does that make more sense? Okay, so another great question. If we don't know exactly where the electrons are in the cloud, how do we know that they're bound within these shells of energy? So we can actually calculate distribution functions, which is a fancy way of saying we can try to calculate the probability of where these electrons are as a position, as a function of position. And when we do that, we can get plots that show us the different regions where these electrons can be. So we do know that shells exist because there's certain areas where electrons are significantly more likely to be, and certain areas where the probability is essentially 0. So that's what allows us to kind of use this depiction where we think of shaded rings around an atom where there's some probability of an electron being in. Does that make more sense? The probability concept is really important, and it's something that you will all go through at the very beginning of Chemistry 1A when you start thinking about quantum mechanics and how that relates to electronic structure. But we're just trying to introduce some of these concepts here just so that we don't incorrectly think that electrons are known to be in certain places. It's always a probability. Okay. Is there an easier flowchart or something like that to write sublevels? So yeah, I'll show one on a later slide that may make more sense. So there's a lot of different ways to visualize them. And I encourage you to look online to try to find some, and we can try to find some more for you too after lecture. So there's a million ways of writing these things. I think I go through like 2 different types in the slides, but if that's not a great visualization, I'm happy to work with you to figure out a better one. Okay. So D and F sublevels will only apply if you're working with an element that actually has those sublevels. So I'll do some examples in a bit, but you'll notice that all of my examples are from atoms that only have S and P sublevels to avoid sort of the D and F sublevels for now. So we can talk more about that after class if you want to understand some of the complexities behind D and F sublevels. But they are really important, and you'll learn a lot about them in Chem 1A.
Yeah, they'll come up in atoms that have more electrons. So
yeah, so as you add more electrons to your atom, you need more sublevels. So then the D and F ones would show up. Okay. And then someone also asked, if you pass the AP exam, can it be used as credit for Chem 1A? So yeah, depending on your score, you can get out of Chem 1A, but it's also worth thinking about whether or not you need a good fundamental understanding of chemistry to be able to move on and take some of the higher level classes in your major, such as material science and things like that. So, we don't want you to close off doors by not taking chemistry, but, we understand that maybe not everyone is interested in it. So feel free to chat with us or the tutors after class. The tutors are really great, and they just went through this, so they may be able to give some advice about having to make that choice. Okay. Any other questions? I'll wait like 30 seconds. Okay, great. So we waited long enough to account for the lag between real time and live stream time. So I'm going to go ahead and move on with the material. Thank you guys for asking so many great questions. I can see that you're all really thinking hard about this, and that really helps us kind of gauge if people are enjoying the material or not. Okay, so now that we have an understanding of energy levels, sublevels, and orbitals, and how they all relate to each other, we want to talk about how you actually fill these electron levels with electrons. So to understand this, we need to define some sort of basic rules of chemistry. So one of the first ones is called Hund's rule. So Hund's rule states that every orbital in a sublevel must be singly occupied before any orbital is doubly occupied. So what this means is that when you go through and put an electron in each orbital, you'd fill up all the orbitals of the same energy with one electron first, and then if you still have leftover electrons, then you would fill an electron into an orbital that already has an electron. We do this because that is the lowest energy situation. Okay, so for example, in this example here, in the 2p orbital, if we just consider the 2p orbital, in the first p orbital we have 2 paired electrons, and in the second and third we have 2 unpaired electrons. So by Hund's rule, this is okay. And here is another example. So in this example, we have 2 paired electrons in the first orbital, and then the second and third orbitals are completely empty. So this actually violates Hund's rule, and this is not a proper electron configuration. So to write this correctly, you would want to have 1 electron in one of the 2p orbitals and the second electron in the second 2p orbital. You would not want to pair these electrons up. So the second rule for how we fill electron levels is called the Aufbau principle. So this states that the lower energy levels must fill before the higher energy levels. So like in this chart here, we have shown the 2s electrons. Those are going to be filled first before the 2p electrons, just because the 2s electrons are defined to have a lower energy than the 2p electrons. So I'll give another quick minute for questions related to how we fill energy levels. Because again, this is like a pretty complex topic and we want to make sure that everyone understands this. We'll do some examples too to kind of help reiterate these concepts. Yeah, so someone asked why the arrows are up and down. So this is because so we didn't discuss what quantum numbers are yet. So the directionality does matter for the arrows because that means you can't have 2 electrons in the exact same place. So you can't have 2 electrons that both are up in the same orbital. You need 1 electron to be up and the other to be facing down because this is the lowest energy configuration. So we can talk about this offline too, because this is a pretty complicated topic that we're happy to discuss further. So for now, just think of the arrows as 2 electrons. So 1 has to be up, and then if you're going to put another one next to it, that has to be down, just because that's the lowest energy configuration. If you had 2 arrows up, that wouldn't be possible. Yeah, so then someone asked if I can show the right way to fill the energy levels again. So I'll go back in the slides. Yeah, so this is the correct way. of filling the diagram. So you would have, electrons in every single orbital before you go and put a second electron into one of the 2p orbitals. Someone also asked why one is a rule and another is a principle. They've just always been called that. I don't know the answer to that question. I think that they're both kind of considered really important kind of guidelines of how chemistry works. But I don't know why someone decided to call one a rule and the other a principle. I think both are similar in that there's something that has to be followed. Yeah. Okay. So someone asked if there is a difference between the two. I'm not sure what that refers to. So if you could please clarify that question, and then maybe I can try to help answer that. And then someone asked for another example of Hund's rule. It's kind of hard to explain without drawing pictures, actually. So I think that maybe what I'll do is I'll send out some more examples of it after class. The main takeaway that we want from this slide is to know that electrons fill from the lowest energy level to the highest energy level. So that means that the lowest energy levels are going to be populated first. And then we're going to start adding electrons into the higher energy levels, just because this is the most stable configuration. And the second main takeaway is that we want to fill every electron orbital with one electron first before we add a second electron, just because, again, that is also defined as the lowest energy configuration. So this is all sort of ways that we help lower the energy of the system to make it more stable. Let's see. So if you were to number the arrows, the one facing down and the first 2p would be the last one. Yeah, that's a great way of thinking about it. Maybe this would have been a great slide to animate. So you would put one up arrow first, and then you would have a second up arrow in the second 2p orbital, then you'd have a third up arrow in the third 2p orbital, and then you would go back and you would put a down arrow into the first 2p orbital. Yeah. Are people still confused about the directionality of the arrows? Okay, so I'm going to take yes. This means that people are still confused about the arrows. Okay, so after lecture today, we can all talk more about that. And I'll find some more examples and we can go through them together. And then if we end a bit early, we can also do that as part of class time, just because I realize other people have commitments and may need to go somewhere else. The main takeaway that we want is that you have to fill electrons from the lowest energy level to the highest energy level, and that you want to pair electrons only if you've already put one electron in that orbital first. These come from a lot of different physics concepts, so these are something that you're kind of gonna have to memorize for now, and then when you take Chem 1A and learn about quantum mechanics, it's gonna make a lot more sense, I promise. Oh, so someone had a question about what's the difference between the Aufbau principle and Hund's rule.
I'm gonna go forward and show Aufbau's principle on this one.
Yeah, so Aufbau's principle just means that you fill the lower energy levels first. So that means that this 2s orbital is actually at a lower energy. So you would if you had electrons, you would put your first electron into the 2s orbital. You'd put your second electron also into the 2s orbital, because the 2s orbital is the lowest in energy. And then if you had a third electron, then you would put that electron into the 2p orbital. Then if you had a fourth and fifth electron, you would also put those electrons into the 2p orbitals. And then where Hund's rule comes in is Hund's rule means that when you start filling those 2p orbitals, you're going to want to put one electron into each of the 3 orbitals before you put any 2 electrons into one orbital. Does that kind of make the difference a bit more clear?
So to sort of summarize that, Hund's rule has to do with what is happening within an energy level. So once we're within 2p, what order do we put electrons in orbitals? While the off-bow principle has to do with differences between energy levels. So when do we go to 2s versus 2p?
Right, exactly. Okay, great. So I'll move on and do some examples. So like we discussed on the last slide, we're going to want to fill energy levels and start filling from the lowest energy first and then fill the higher energy levels. So the electrons closer to the nucleus are more stable and have a lower energy. So as we started filling them, we would put them in the S shell first, and then we would just go around and you'd fill successfully higher energy levels. So this is an examples of off-Bow's principle, right? Because if I reverse the animation, just like off-Bow's principle states, you would start filling from the lowest energy to the highest energy first. And by definition, the lowest energy electrons are close to the nucleus. So just to go over that one more time, you would fill them this way. Hopefully this animation helps make things a bit more clear. Okay, and so another way we can represent this is actually using lines instead of dots around an atom. So we can plot it as a function of energy on the left, and then we can have our first energy level, n equals 1. We can have our n equals 2 energy level and our n equals 3, and then we would do the same thing where we can just populate all of the electrons. So that's another way of representing the same thing that I represented with all of the dots around the atom. So that's another representation that could make more sense to you. Okay. So now we're going to define some terms. So first we want to define what the valence electrons are. So the valence electrons are the electrons in the outermost shell. So here in the blue shading, I have shown the outermost shell. So these electrons would be considered the valence electrons. The core electrons are the electrons in the inner shells. So those would be all of the ones that are right before the valence electrons. So here I have shown the first and second rings shaded in blue, and so those make up the core electrons. Okay, so now as a quick question in your groups, based off the following atomic model, how many core electrons are there? And then how many valence electrons are there? So take a few minutes in your group to think about this, and then also continue thinking and asking questions about electron pairing and Hund's rule too. And then we'll come back together in like 3 or 4 minutes and talk about it. I also just sent everyone a link in their Zoom breakout rooms with a link to a website that also explains Hund's rule and Aufbau's rule with some different pictures. So if you are still confused, reading through that may help. And it also discussed some of the basics of pairing of electrons too. Okay, so if we are given the element name, would the core electrons be equal to the atomic number of the element? So if we're only thinking about neutral elements, then the number of electrons has to equal the number of protons. So the number of protons would have to equal the total number of core and valence electrons. So the answer would be no. The number of core electrons does not equal the atomic number, because we know that the atomic number equals the number of protons, and the number of protons equals the total number of electrons in the molecule, not just the core plus the valence electrons. Okay, do you guys need more time? If so, let me know. Otherwise, we're going to start going over the answer in 30 seconds. Okay, so someone asked if the inner shell is only the first shell or is it both the first and second? So the core electrons are defined as all of the electrons that are inside the valence electrons. So then the core electrons would be both the first and second shell. Yeah, so that's just the definition. Hopefully it'll make more sense when we go over the answer too. Okay, so someone said they needed more time, so we'll give you another 1 to 2 minutes. Okay, so someone asked, why is the energy weaker in the first orbital? Wouldn't the electrons be attracted to the protons since they're closer compared to other orbitals? So that's a great question. So when we say that the lowest energy levels are closer to the nucleus, it actually means that they're very tightly bound, and that's what makes them to have low energy. So when we think about energy in terms of atoms, the lower the energy often means greater stability. Yeah, so the electrons are very much attracted to those protons that are right next to the nucleus, and that's what makes them have such a low energy. Does that make sense? Yeah, so the main takeaway is that we can't say that the energy is weaker, we just say it's lower, and that's a definition.
And that means the attraction is stronger, not weaker.
Right, yeah, so in the context of atoms, lower energy is good. It means the atom is more stable, and it means that it's stronger. Okay, so I'm gonna go ahead and move on with this question for the sake of time. Okay, so if we count the number of core electrons, which are just the ones in the first and second levels, we can see that there are 10. So there's 2 in the first level and there's 8 in the second level. So this gives us a total of 10. And then I've shaded all of the valence electrons in orange. So there are a total of 4 valence electrons. Okay, so someone asked, does it go cloud, then shells, then sublevels, then atomic orbitals? So would kind of, yeah. So there is like the entire electron cloud around the nucleus, and that whole cloud is represented as these different shells or regions that electrons may be in. And then inside each region, there are different sublevels, and each sublevel contains a certain number of atomic orbitals. Okay. Great. So we've talked a lot about the periodic table during this class, and the electronic configuration actually does relate to the periodic table. So we can identify the energy level and sublevel from the periodic table. So we'll go through an example on the next slide, but right now here on this table I've labeled the S blocks, the D blocks, the P blocks, and the F blocks. So again, in this class, we're only really thinking about the S and P blocks, just because as we move to D and F, things can get a bit complicated and we just want to introduce some of the basic concepts here. But just from looking at the periodic table, you should be able to identify what energy levels you are, but we'll go through an example in a second. Okay. So we can use the periodic table to count the number of electrons. And like I said, we're only consider the main group elements for now. So just to zoom in on that. Okay. Someone asked, why is the number of valence electrons not equal to the entire outer shell energy level? Okay, so let's go back real quick. So the shaded circles are how I represent something that's filled. So then the ones that are white with the blue outline, I mean that there's no electron there. I'm just trying to represent that as like there could be an electron there, but there's not. So that may have been a confusing representation for some people. So think of those 4 white dots as those are completely empty. Those are not electrons.
So like empty slots.
Yeah, so those are completely empty. So that is why there are only 4 valence electrons, because there's only 4, if we go back further, there's only 4 filled in blue dots. I hope that clears up the picture. Okay, so if we're only going to consider the main group elements for now, and we have level 1 at the top. So this is how I can use this is how we can use the periodic table to help figure out what energy level we're in, is that we define level 1 to be the very top, and then level 2, the second row of the periodic table, that is the second energy level. And then the third row denotes the third energy level. So let's try to represent this in a different way. So we can also plot this as a function of energy. So we know that the lowest energy ones come first, and those are going to be all the way at the bottom. So this is the n equals 1 level. It's the lowest in energy. These are the ones that are closest to the nucleus, and they're the most stable because those electrons that are right next to the nucleus are going to interact very strongly with the positive charge of the nucleus. And then on the second row, we start to get the second energy level, and then we get the third energy level. And if we go across the periodic table, we can also count the number of electrons in that element because we know how many protons there were. For hydrogen, we know there's 1 electron, so it has 1 electron in the n equals 1 level. Helium has 2 electrons because it has 2 protons, so that's how it gets its second electron in the n equals 1 sublevel. And then we can keep going. And as we add more and more electrons, we keep successfully filling up these levels. Hopefully this is a better way to visualize how this actually occurs. So basically you can use the periodic table to count how many electrons are in your element, and then you can relate that to which energy level you're in by looking at the periodic table. So for example, for nitrogen, we know that we have 7 electrons. We know it's on the second row of the periodic table, so that it must populate electrons all the way into the second energy level. And then from reading off the periodic table, we know that there must be 2 electrons, and that equals 1 level, and that the other 5 have to be in the second energy level. So we wanted to briefly discuss more about valence electrons. So valence electrons are really important to understand because they often dictate reactivity and are involved in the formation of bonds. So someone asked about bonding in the chat, and this is a great question because we're going to talk about bonding tomorrow, and a lot of these concepts are going to be really important. So here visually we can think about 2 atoms approaching each other to interact, and this is a great way to visualize why we care so much about the valence electrons, is because they're the outer levels, so they're going to be the first ones that are able to interact. So someone asked where the D block was in that image. That was because before I said we're only going to focus on some of the main group elements, so I just copied and pasted it out just because that was easier to read, because otherwise the periodic table is pretty large to have in an image. So that's just an editing thing on my part. The D block definitely exists, and it's definitely in the middle, but since we were only talking about S and P electrons, I just cut it out just to make my slides look, or just to make you, so that you could see the periodic table, because otherwise it's so big. Okay. So we can represent the valence electrons of an atom or molecule using Lewis structures. So I'm going to quickly go over the procedure for drawing a Lewis structure while doing an example. So let's think about drawing a Lewis structure for the element aluminum. So first, you'd want to determine the number of valence electrons that aluminum has. So like we discussed, you can actually read this off the periodic table. So aluminum has 3 valence electrons. If this is confusing, just think about how we drew it before, and feel free to write out where the different electrons are. And then if the atom is charged, add or subtract electrons to get the correct overall charge. So in this case, we're talking about a neutral atom, so that's not really relevant for us, but you could think about being asked to draw a cation or an anion that has some charge. So then you would want to add or subtract electrons to get the right total charge. We'll do an example of that later, since that is more complicated. And then you would want to draw in dots to represent electrons while accounting for Hund's rule. So what this means is that we would put 1 electron on one side of the aluminum first, then second electron on the top, and then the third electron all the way on the end. So we would not want to put 2 electrons next to each other, because that would violate Hund's rule, like we had discussed before. And then you would also want to include overall charge if necessary. Since this example is neutral, then you wouldn't have to write anything. But if it had been a cation or an anion, you would want to put a plus or a minus in the corner, just to represent to other people that that is in fact a charged species. So we're running short on time, so we had one quick question that you guys can think about. So if anyone has to go, feel free to do so, or you can work in your breakout rooms to draw the following Lewis structures. So the first one, you want to draw the Lewis structure for nitrogen, and for the second example, you want to draw it for a fluorine anion. So note that in the second one, it actually has a charge. And then what we'll do is we can also pull you back into the main room in a few minutes too, so you can ask general questions. Okay, so for the sake of time, we're gonna just go over these answers, but then, oh, someone asked if I can go back to the rules. So yes, here's the rules in the example. So I'll leave this up for a few minutes so that you guys can have a chance to do it with the rules. Okay, now that the rules have been up for a minute, I'm gonna move on and go over the answers quickly. But again, we know this has been rushed, so feel free to stay after lecture, and Lorena and I will both be here to answer questions. Okay, so for the first one, nitrogen has 5 valence electrons, so you would draw the Lewis structure for nitrogen like this. You would have 5 dots surrounding nitrogen. And then for the fluorine anion, fluorine naturally has 7 valence electrons, and since this is negatively charged, you must add 1 electron to account for that negative charge. So that means that now this atom has a total of 8 electrons, so you would want to put 8 electrons around the fluorine. And then you would want to have the little negative sign in the corner just to denote to everyone that it is like a negatively charged species. Okay. So feel free to continue posting in the live chat, but now this is the end of lecture, so please stay in the Zoom room for our office hours. So because of the lag, we'll pull you back in like 30 seconds, but keep using the live chat until then and we'll keep monitoring it.